Good morning. You're in Jasmine, and this session is Denial of Service with a Fistful of Packets, Exploiting Algorithmic Complexity Vulnerabilities by Nathan Hauke and David Renardy. But first, we have a few announcements. The Black Hat Arsenal is in the Business Hall on level 2. There's a mimosa event at 11:50 and an ice cream social at 3:20 in the Business Hall. Lunch is in Bayside AB from 1 to 2:30. And don't forget the merchandise store on level 2 and session recordings from SOC. They have a desk on every level. Please silence your phones. And without further delay, please welcome Nathan Hauke and David Renardy.
Thanks for that introduction. Good morning, everybody. Thank you for coming. My name is David Renardy, joined by my colleague Nathan Hauke. And we're going to talk to you guys today about algorithmic complexity vulnerabilities and how you too can cause denial of service with only a fistful of packets. So Nathan and I are both security researchers at a company called 26 Labs. We work in vulnerability research, cybersecurity. And I know you guys are really here because Nathan's bio mentioned he's a broomball national champion. But please hold any broomball related questions until after the talk. Okay, so what are we going to talk about today? So I'm going to start off with a recap of what algorithmic complexity vulnerabilities are, how they present themselves, some historical examples, and then we're going to launch into 3 new algorithmic complexity vulnerabilities that Nathan and I discovered over the past year. And then we're going to wrap up with some defense and mitigation techniques, and we're going to introduce ACsploit, which is an open source tool we helped contribute to that we'll be presenting at Arsenal shortly after this. Okay, so what's an algorithmic complexity vulnerability? So what we're talking about is a resource exhaustion attack resulting in denial of service. And the cause for this is you have some back-end algorithm that's processing some user input, and it has unacceptable worst-case performance. And that worst-case performance could mean a couple of things. You could exhaust CPU resources, which we call an AC time attack, or you could exhaust some space resource, either disk space or RAM, which we call an AC space attack. Just to give you an idea, this is kind of a toy example. You could imagine some server somewhere, they implement insertion sort on user submitted input. And they might do this because they think, hey, our users are really nice and they usually submit sorted data. And in the sorted case, insertion sort takes a linear amount of time, so it's relatively efficient. They wouldn't be considering that an attacker might submit a reverse sorted list, which would have quadratic time and could cause denial of service. Okay, and this is kind of like a silly toy example. There are way better sorting algorithms, but this gives you the kind of idea of what Nathan and I were hunting. So we're trying to find these corner case inputs that generate the worst case performance for some back-end algorithm. And I'll note here that a lot of the ways that we typically use for exploring input space, like fuzzing, don't necessarily find these kinds of inputs. So I want to give a little bit of motivation for why we're talking about this, because I think algorithmic complexity vulnerabilities have been around as long as people have been implementing algorithms. But we feel that there's kind of a gap in awareness that's affecting the community. And it's sort of at all different stages. So you have application designers who maybe aren't considering the risks of algorithmic complexity vulnerabilities when designing applications. Developers and pen testers not incorporating algorithmic complexity vulnerabilities, like known vulnerabilities, into their test suites. And then vulnerability researchers, we've noticed this problem where vulnerabilities are discovered, and because of the CVE cycle and sort of how vulnerabilities are talked about, they're not tied to like new applications. So we see the same vulnerabilities come up again and again and again. And so Nathan and I come at this from a little bit of a unique perspective. We spent the past 3 years working on this research program called DARPA Stack. And part of the point of that program was to hunt for algorithmic complexity vulnerabilities. So DARPA would make these kind of challenge problems where they'd give us a program and they'd ask very pointed questions. Is this program vulnerable? And what would you need to exploit it? So we spent 3 years working on these toy programs, and that program wrapped up earlier this year. And we were curious, how hard is it to find these things in the wild? Just to make sure we're all on the same page here, when you mention denial of service, a lot of people initially think, oh, DDoS, like that's denial of service. And I just want to contrast how AC vulnerabilities sort of work compared to distributed denial of service. So in DDoS, you have some botnet, and basically you have a bunch of bots, they're communicating with the server, and you get denial of service because you have so many bots trying to connect. So the effort that you're putting into this attack is sort of reflected on the server, giving you the denial of service effect. And this is expensive. You need a large botnet to do this. In contrast, an AC vulnerability typically is a relatively compact payload, like a fistful of packets, submitted by a single user. And you get the same denial of service effect on the server. So AC vulnerabilities are much cheaper than DDoS. Additionally, they can be a little quieter than DDoS. Algorithmic complexity vulnerabilities are a design problem. They come out of intended functionality, right? That's how the program was implemented. So they don't present themselves the same way that other denial of service effects present themselves. You're not necessarily going to get tons of error messages or excessive logging or unusual traffic. It's a regular user interacting with your service. And this can make some algorithmic complexity attacks kind of insidious. You could have a payload that is designed to cause denial of service for 2 minutes or 5 minutes. And then once the algorithm completes processing it, the normal functionality resumes. So we've seen even security researchers ignore symptoms of denial of service or algorithmic complexity attacks and think that they're just some sort of anomaly, right? You just turn off the server, turn it back on, and everything is fine. This isn't something new. Again, this has been around for a long time. I just want to highlight there's some talks in recent years that you maybe have seen that highlight algorithmic complexity vulnerabilities. So in 2011, Klink and Velda discovered that a bunch of hash table implementations were using linked lists to resolve hash collisions. This is a bad idea because it's really easy to create hash collisions. So you can basically submit a bunch of HTTP parameters, for example, that all collide and cause that linked list to grow. More recently, in 2016, Kara Marie gave a talk here at Black Hat about decompression bombs. So a decompression bomb is a natural corollary to having very efficient decompression algorithms. So if you have an efficient decompression algorithm, then you're going to have some small input that decompresses to some huge size, causing like a space effect. Also in 2016, Eric Davison gave a talk about revisiting regular expression denial of service. Let's dig into RDOS real quick, sort of explain what's going on there. So in RDOS, you have some regular expression, and you want to parse some candidate string. And a typical way of representing your regular expression is through some finite automata. So in this case, we have an NFA that's generated by that regular expression in red. And you'll notice that there's some ambiguity in that NFA. So there are multiple outgoing arrows that represent the same character. So when this NFA parses that candidate string, AAAAB, it's going to pick some path through this NFA. When it hits that B, it's a non-matching string, and it's going to say, oh, wait a minute, I maybe took a bad path. So it'll go back, it'll revisit all those potential paths, and it'll end up traversing all 16 of them. This could be a big problem if you have more A's in that string, and you can get denial of service that way. And this has been known for like a decade at this point, so you'd assume that we've got this pretty well handled. Not so much. So in just 1 month ago, Cloudflare went down on the East Coast for about half an hour because of a RDOS issue. And then 3 years ago, Stack Exchange went down because of this regular expression that tries to parse out white space from entries. Some nefarious user figured this out and basically submitted a post to cause denial of service. And in a minor miracle, they were able to recover in half an hour without being able to Google the symptoms on Stack Overflow. Okay. So I just want to give you guys a little bit of some background into sort of how we were approaching some of these problems in Stack. So one thing that we were trying to do is we were trying to find common algorithmic complexity vulnerabilities for standard file formats. So we were hunting for like decompression bombs, et cetera. And in doing so, we started looking at PDFs, file format that we all use. And we ended up discovering something kind of interesting there, which is a time attack against PDF parsers. So imagine you're trying to parse the content of some PDF, you're trying to extract the content. We have a way of constructing PDFs where you get a time attack against that parser without going over a certain memory ceiling. So this isn't quite a decompression bomb, right? The name decompression bomb signifies this explosion of data. So that's not what's happening here. You have this time effect while using a sort of relatively small amount of data. So bomb is maybe not the right word. We decided napalm was more appropriate. It's sort of this long burning fire, right? It's going to keep consuming that CPU resource without ever using the memory or consuming too much memory. So So we approached this starting with a traditional decompression bomb. So DGR Stevens wrote a blog post in 2008 about these PDF stream objects, which are in the PDF specification. And he noted that these can be used to construct a traditional decompression bomb within PDF. Basically how that works, PDF stream objects are pretty simple. You have some data in blue, and then you have a set of filters in red that operate in sequence on that data. So the output of your first filter goes into your second filter, so on and so forth. And what Stevens noted is that within the PDF spec, one of the defined filters is flate decode. Flate decode is a decompression algorithm. It's a companion for deflate, which is used in PNG, zip, gzip. It's a common compression algorithm. So it makes sense for them to have chosen to include this just for decoding some random data. But of course, you have this efficient decompression algorithm now, so you can make a decompression bomb. Moreover, Stevens noted that because you can stack these filters one after another, you can actually get like a nested decompression bomb because flate and deflate are block-based. So you actually end up getting a magnified effect if you compress a low entropy input multiple times. So we implemented this bomb. In fact, I think we're the first people to actually implement this bomb. So he describes how this bomb would work in his blog post, but we could not find a POC anywhere on the internet. Which of course meant that every PDF parser that we looked at was vulnerable to this bomb. But we noticed a couple of things while we were looking at it. So the first is that when you do this decompression, that decompression causes a small time effect. It's going to take a couple of seconds to decompress that data. The other thing we noticed was that in the PDF spec, you can put as many of these PDF stream objects into a single page as you'd like. There's no constraints on how many PDF stream objects you can put there. And in fact, you can pass them by reference. So you just like put a little pointer to where your PDF stream object is and it'll load another PDF stream object. So our idea was maybe there's a way for us to put a bunch of kind of small decompression bombs into a single PDF, have them loaded one after another and cause some sustained time effect, right? Have each one of those bombs take a little bit of time and then sort of have a bunch of them cumulatively cause a large time effect. So how can we translate this AC space attack into an AC time attack? There's a little bit of a problem here. The problem is that when you're loading those decompression bombs in a single page, typically you want to display the whole page, right? So if you're loading each decompression bomb into a single page, then eventually you're going to have a cumulative buildup of the memory. And eventually you're going to run out of memory on that process. So our idea was, let's see if we can't find a way to free up that memory. If we could somehow free up the memory used by each of those decompression bombs, then we could have a graph kind of like the one displayed here, where you're deflating, causing this, or sorry, you're flating, causing this growth in the memory, but also a time effect, but then you free up the memory. And so then you're able to repeat this process over and over again and get a sustained time effect against the server. So we're gonna go back and we're gonna look at more of the filters available in the PDF stream specification. You might think like, okay, is there just like a deflate decode, like an opposite where you can compress the data back down? And you can't. There's no like inverse set of filters. But there are some filters that will shrink the data that you give it. So this is a pretty sensible filter. It's called ASCII hex decode. And what it does is it takes pairs of valid hex characters and converts them into their ASCII equivalent. So here I've got some ASCII or some hex characters converted to the word smoky. And so our idea is we want to use flate decode to grow some decompression bomb. That's going to take a lot of time. But then if at the end of that process we run a bunch of ASCII hex decode filters, we can shrink the size of that stored data. Because each time you run ASCII hex decode, you're reducing the size of the data by a factor of 2, right? 2 bytes give you 1 byte of output. The problem with this is that you need valid hex characters to hand to ASCII hex decode, right? If you don't do that, then the parser will throw an error. So we're looking for some kind of like almost fixed point behavior where we pass it hex characters, we run ASCII hex decode, decode it as ASCII, and get back valid hex characters. This might seem like kind of a challenging problem. It's like, how do you sort of think through these cycles? But it actually is pretty easy once you learn this one weird trick. It turns out that in the ASCII encoding, through total coincidence, the character 3 has hex encoding 3-3, which means if you start with a string of all 3s, you run ASCII hex decode on it, you're going to get back a string of all 3s, again, of half the length. So if you start with a string, let's say of length factor power of 2, then you can eventually reduce the size to a single byte. So this is what one of these little fires looks like. You've got your data, and you've got a set of filters. You're starting by using flate decode to grow that decompression bomb, and then you're running ASCII hex decode to shrink the size of the data. It's cut off here. You can see there are 6 ASCII hex decodes in the set of filters, so that would reduce it by a factor of 2 to the 6. And if you add another one, it'll keep reducing it. So this gives us a sort of recipe for creating PDF napalm. So you start by guessing whatever the RAM limitations are of the system you're attacking, and you don't have to have a type bound. Just guess something reasonable, maybe a gigabyte, 500 meg, something like that. You then deflate a bunch of 3s, and then you encode that into a PDF stream object with flate decode filters to unpack it, and then ASCII hex decode filters to crush down the memory. You then take those PDF stream objects and you fill a PDF page with references to that PDF stream object. And that's going to give you that sort of sawtooth graph we saw earlier, right? It's going to take some time during those flate decodes, and then in the ASCII hex decodes, it's going to free up all that memory that you're using. So let's take a look at a demo here. Oops. Okay, so on your left, we've got a simple Java program. This is written using iText, which is a Java PDF parsing library. I'm not picking on iText here. Again, this is a problem in the PDF specification itself. It's not an implementation bug. And basically what we're doing here is we're just extracting the first page of this PDF, and we're just trying to get the contents of that first page. And I've got some timing information here that we're going to look at. So I don't script commands. First, we're going to run this program on basically the skeleton of a PDF. This just has all the necessary headers that you'd want on a PDF. There's nothing in it, okay? It takes 16 milliseconds, so it's pretty fast. Let's take a look at Didier Stevens' traditional decompression bomb. So this is the space effect. Okay, it's going to take a few seconds here. And you'll notice that this is a pretty small file. Okay, so we eventually got an out of memory error. So this file was only like 1,800 bytes, so pretty small. And we were giving the JVM 2 gigs of heap space. So this is really small. I don't know if you guys mess around with PDFs at all, but they're big, like typically megabytes, hundreds of kilobytes in size. So you could easily hide this in an existing PDF and no one would notice from the size difference. So that's your traditional decompression bomb. And now let's look at our bomb, our napalm here. Okay, so it's again relatively small, under 5K. And as soon as this updates, you'll see we've hit 100% CPU utilization. This will stay at 100% for the next 10 minutes. And like I mentioned earlier, these are configurable. You could easily extend the effect at a small cost to the size of this bomb. Okay. So what's the impact here? So we looked at a bunch of spec compliant implementations, and I want to reiterate this. This is a problem in the PDF specification itself, right? The PDF specification says you have these PDF stream objects, you have these filters, you should respect them. It's not that interesting to cause denial of service to your local PDF, Adobe Acrobat or something. You just close it and go on with your day. It's a bigger deal if you're trying to parse PDF server side. So why might you do that? Why might you accept the PDF from a user? We looked at a couple of different OCR applications. So one use case is you have an accounting software and you want to allow your clients to submit receipts, and you're going to use OCR to pull off line items from those receipts. So we actually identified several applications that do this, and they're all vulnerable to this attack. So we contacted these vendors, went through responsible disclosure, and we came up with a handful of mitigation techniques. So the first thing that you can do is deviate from the PDF spec and institute some input sanitization. So specifically for our attack, if you disallow repeated filters, then you can't attack it. You could also limit the number of PDF stream objects in a given PDF page, there's no reason to have 100 or 200 or 1,000. But this might not cover all the potential ways that you could generate this kind of effect. So really the safest thing to do is to institute hard resource controls, especially for some server-side application. You don't want a PDF that takes you 10 gigabytes of memory to load. You also don't want a PDF that takes you 10 minutes to load. So if you just set hard caps on runtime and memory, then you can avoid some of these problems. Okay. And we're going to see these themes sort of come up again and again in the other vulnerabilities, which Nathan will talk about now.
Thank you, David. The next vulnerability I have to share with you today is an unauthenticated vulnerability in open source Linux VNC servers. And unlike the AC time effect, which we just saw, we're going to be generating an AC space effect this time. To make sure we're talking about the same thing, what is a VNC server? All you need to know is you remotely access the computer, get a graphical view, and for Windows users, it's like RDP. A common use case would be if you're a system administrator and you want to access all of the computers in your network, make changes from the comfort of your own desk. So let me set the scene for you. I'm sitting at my desk and working on a project, and my VM is out of memory. This is weird because it's 32 gigabyte hard drive, and I'm not doing anything particularly memory intensive. So I go and check it out, and there's one file. It's a VNC log file, and it's 30 gigabytes large. Like, why is this file so large? But one thing I could do is just delete it and get on with my work. But I was thinking about algorithmic complexity vulnerabilities and looking at it, and this just didn't seem right. So I took a look at the file and saw something like this near the top. And you can see here that there are these lines printing other clients, and each one has an additional IP address in it. I said, aha, this is an algorithmic complexity vulnerability. I can make the space on this file grow quite large. And the idea for this was to just add additional connections and make each of these lines longer and longer. So to investigate this, we went into the code and found this chunk. Found this because you can see the other clients line being logged here. And this chunk of code is called every time there's a new connection to the VNC server. And sure enough, there's this for loop here, which is printing the IP address of every connected client. So there's no limit here. It's not going to stop after 10 or 20. There's no limit. So pretty simple recipe for growing the disk space here. We can create multiple TCP connections to the server. We're going to keep those connections open, because if you allow one to close, then the number of connected clients goes down and you don't get the same growth in the file. But as long as you keep these connections open, each one is going to add a longer line to the log file. And you might say, each one's only 11 or 12 bytes larger for the IP address. But if you do this enough times, you're getting a quadratic effect given the number of connections. So let's take a look at how this works. To get you oriented, on the left side, you've got a black screen that's showing the log file for a VNC server that I've got up. The red is showing the current size of the server in bytes, and we've got the CPU showing in the bottom right. So first thing I'm going to do is just connect to this VNC server. And notice I have to input a password here. But once I do that, I can connect to this VNC server, and you should see some logs showing up here on the bottom. So now what I'm going to do is make some netcat connections to this. So 20 times, I'm just going to connect to localhost 5901, which is where this is running, and sleep a second so that you can see what's happening on the logs. So very similar effect to what we saw before, these other client lines getting longer and longer. We've already got 7K and growing of input. So once this finishes, though, that was only 20. Let's do this many more times and see how large we can make this file. So I'm going to remove the statement, the sleep statement, so we're not here all day, and do this 800 times. You can see as we saw from the code that there's no limit on this. Just each time it's printing a whole bunch of IP addresses in a big block. And we're now up near 4 megabytes of input. The logical question next would be, can I do this 8,000 times? And you would think maybe you can, but in fact you can't. The reason for that is a kind of bonus vulnerability that we found when looking at this. And this one's not really an AC vulnerability. It causes a similar AC effect, but this one's more of a bug. But it causes infinite logging and denial of service to the VNC server. So here's some definitely not vulnerable code that's getting called each time you have a new connection to the VNC server. And some things to highlight here are that there's this sock, the accept call is returning a file descriptor. And if this were for some reason to fail, you would print a logging message to the log file. So I said it's not vulnerable, but maybe it is. So what happens if we run out of these file descriptors? Because we're giving one out every time there's a new connection. Well, the answer for accept, if you look in the man pages, is it'll give you an EM file error. Now, if you get an EM file error, we were just returning from that function. But there's still this new connection out there that needs to be processed. We haven't fulfilled that requirement yet. And if you have a new connection waiting to be processed, well, what do? Well, you call that same chunk of code. So it's like, hey, there's a new connection. And like you realize, oh no, there's too many open files. But like, hey, there's a new connection I need to process that's still out there, and so on and so on. This doesn't really stop. So the recipe for exploiting this disk space and time is the same steps as before. We're going to create the two connections, the TCP connections, keep them open. We're going to repeat this until we're out of file descriptors. And for our testing, that was around 1024. If your U limit is higher than that for some reason, you actually hit a different error condition that we're not going to talk about. But assuming 1024, your next connection attempt triggers an infinite loop that I was talking about. And I want to highlight here that this isn't like the previous case where we were sending one connection and getting one line to the log file. It's one connection and getting infinitely many lines to this log file, or at least until you're out of disk space. Now let's go back to our demo. We've sent about 800 connections. I'm going to send 250 more just to get us over that 1024 limit. And we were at 4 megabytes. We should see here, there you go, this infinite logging of as fast as it can, printing out these log messages. The CPU is now up near 100%, over 100%. And we're growing this log file at a megabyte every few seconds, kind of as fast as this computer can process them. And if we go back to our VNC server and try to connect, we'll confirm that we have indeed achieved denial of service here. You can't get additional connections to this VNC server. So what are the impacts? If you were watching really closely, you might have noticed that these log files that we're printing out were not the ones that were shown in the code there. And that's because I was showing you a demo from Tight VNC, but code from Turbo VNC. And what we found was that the VNC servers, kind of legacy servers that are out there, all played some giant game of telephone somewhere down the line and shared these chunks of code with each other. And so this vulnerability persists across multiple VNC servers that we looked at. Another thing I want to highlight is that we saw that my VNC server had a password, and I never needed that, any kind of credentials for this VNC server, just the ability to connect to it. So I was sending 1,000, a handful of fistful of three-way handshakes and achieving denial of service. So we went through the responsible disclosure process with these VNC servers, and some of the solutions we came up with were first an algorithmic change, so just not logging the list of other clients. And the reason for this was that we had enough information from other things in the logs, when clients were connecting and when they were disconnecting, to recreate this list of other clients if we ever really needed it without printing out 800 IP addresses at one time. The other thing you can do is an input sanitization effort, limiting the maximum number of client connections that are allowed to your VNC server at one time. So you probably don't need 1,000 people accessing the VNC server at the same time. So let's jump ahead now to the final vulnerability we're going to talk about. And this is an unauthenticated denial of service in Dropbox's password strength estimation tool called ZXCVBN. It's the bottom 6 letters on the keyboard. So what is this tool? It's designed to replace some of the archaic password policies that we use now that are like, you need a capital letter and a lowercase letter and a number and some special character. So we've known for a long time that we can still create, and people do create, really weak passwords using these policies, like ABC123 exclamation point. Fits all the parameters, not very strong. So what ZXCVBN tries to do is create a measure of how difficult it's going to be for an attacker to actually guess your password. And one of the things they decided an attacker was going to do was have a list of all of these commonly used weak passwords and go through those, among other techniques. So any password that's commonly used is already is rated weak by this service. Now, let's take a look at how it works. Let's say I have my name up here and a common password and today's date, and I put those together as a password. This tool is going to parse all 3 of them and break it up into these 3 chunks, and then we're going to analyze how these work and give a score for each of these 3 independently. So you'll notice that the first one is recognized as a male name. Password belongs to the dictionary called passwords, which is a list of common passwords. And then the third part is recognized as a date, 8/8/2019. And each one of these gets a score, and to get a total score for your password, you combine these. And we're making a conservative assumption here that the attacker knows the exact structure of your password, but not the exact contents. And so that's how you can combine these 3 scores to get one score for how strong your password is. One thing I want to highlight here is that I put an @ symbol in my name, but it was still somehow recognized as Nathan. So let's take a look at how that worked, how they took the @ sign and turned it to an A. So this leet substitution algorithm, let's take the example of password. I've used an @ sign and a 0 in place of A and O. The Dropbox tool is going to go and look at its table, predefined table of leet characters, and find the @ sign and the 0, and find that those are replaced by A and O. It'll make that replacement, so we're back to the word password. And that's when it's going to do the dictionary lookup to find whether this word is in its list of dictionaries. Password will be in the common list, and we'll rate that this is not very strong. Another thing that happens is that password, it's not just looking for the word password. This is a quadratic time algorithm looking at every single substring of your password in case you had 2 words put together or something like that. Let's look at a second example, black hat, but I've used a vertical bar and the @ sign again. The vertical bar is special because it can be replaced by an I or an L, according to Dropbox's tables of characters. So we need to look at both of these possibilities in order to determine the strength of our password. So in the first case, we get black hat. This is not a real word, and so it's not as bad as password. Doesn't show up in any of the dictionaries. But then we look at replacing the vertical bar with an L, and we get black hat instead, and that is in the list of common passwords, so stop using black hat as a password, you guys. That gets a bad rating, and we take the 2 scores, we take the worst of these 2 scores and determine that black hat is not very strong. So notice how we had to do kind of twice the work here in order to figure out how strong our password was. And there are actually 3 of these characters that are ambiguous. There's the vertical bar, the 1, and the 7. So we asked ourselves, what happens if you put all 3 of these together? And in fact, you don't get twice the work now, you get 8 times the work. So you have to look at all possibilities for the different replacements for each of these 3 characters. So for each of these 8 possibilities now, we make the replacements, we get 8 different words. We put these 8 words through the dictionary match, which is again a quadratic time algorithm looking at the substrings of every single one. And then we find that lollipop is in there, which is not strong, so it's only one of those 8 is weak, but together, we take the weakest of those. So we've done 8 times the effort now from what we would normally do. So we asked ourselves, what's the worst that can happen here, putting together some of these things? The first thing is that I've said a few times now, it's a quadratic algorithm. We're looking at every single substring of the password. So we're just going to make our password as long as possible. Then we have these 3 special characters, which have multiple possible substitutions. So we're going to use all 3 of those. And finally, we'll now have 8 replacement tables, and we're going to make all 8 of those replacement tables as large as possible by putting in every other leak character. And when you put all 3 of these requirements together, you end up with a password that looks something like this. Dropbox asked a similar question of what's the worst that could happen, but they really looked at what the average case was, because they took a list of common passwords, like 30,000 of them, and ran their tool against each of those passwords and found the worst case to be about 100 milliseconds. And they recommended, because they knew that making longer passwords would make it run longer, to cut off the password at 100 characters, but there's nothing in their library that actually enforces that. So when we ran our worst case password, we found that this actually took almost 6 seconds in the 100 character case, 24 seconds for twice that many characters. And for a 1,000 character password, it took over 22 minutes. Now, there's no reason that we had to stop at 1,000 characters other than we got kind of bored running this, and waiting for quite long amounts of time. Let's talk about the impact a little bit. It was initially written, this tool, in CoffeeScript, but because it is a really good tool and it's the only one that does this sort of measurement, it's been adopted by a lot of different programming languages and implemented in many different programming languages. And you'll notice here that some of these programming languages, unlike CoffeeScript, are made to be run server-side, not client-side. This also shows up in a number of enterprise software. So Dropbox is one, and we also went through the responsible disclosure process with Stripe and JetBrains. So some big name companies who are using this, and they're using it on their user sign-up page. What this means is that you can go to a user sign-up page and put in a password without having any credentials for that server. And if you're running this server side, then that'll get sent to the server and they'll measure how strong your password is. And if they're not doing any other kind of mitigations, then this will run on their server for 22 minutes or however long it takes on their servers. And one of the reasons you might do this server side is because if you actually want to make sure that your users are giving you strong passwords, then you want to verify it server side. Because someone could get around things client side. It could warn you that you don't have a strong password, but you could submit it anyway. So that's why you might check server side whether or not they've given you a strong password. So we have a demo for this. What I have here is a Docker container. I'm not attacking any live version of JetBrains right now, but we have JetBrains in a Docker container locally. We have the CPU here, and this is the user sign-up page. So again, I have no credentials on JetBrains. but I'm going to sign up as a user here. And without putting in any other identifying information, and I don't have to submit a full completed application, I can just copy this password. Before I paste it in, I'll just point out how quickly you get a response for fair, strong, if I'm just typing in some small password. So it's generally very responsive and has limited impact on the CPU. But now if I paste in this password, we'll see the CPU go up, and notice how we don't have any kind of review of how strong this password is. And this effect will last for quite a while because we've used the 1,000 character password. The other thing I'm going to do here is add some extra characters to resubmit this password a few times, and then we'll see what happens to another user in a different tab. So just add some more characters. Add to the load here, and then I've got a valid user who is trying to sign in at the same time. And they can put in their password, and they're now not getting any feedback on how strong that password is. They might not recognize this and can put in the second password and try and register. But good luck to them, because this server is going to be working very hard on processing my malicious password for quite a long time. The same effect would happen if you were trying to log in and already had credentials and were trying to log in as a legitimate user. So some of the things you can do, I mentioned that Dropbox recommends cutting off the input at 100 bytes. You could set some threshold using input sanitization to say, if you've given me a long password, I'm just going to evaluate the first part of it. But that may not be enough, because we saw even with 100 characters that this could take up to 6 seconds. And so 100 milliseconds, if you're expecting 100 milliseconds, something 60 times that may not be acceptable for your servers. If you're getting a lot of these requests, that can have a high cost. Another thing you can do is have better algorithms. So this dictionary match looks at every single substring of the password. I don't think it needs to. You're not going to find a dictionary match on the first 999 characters of the password if you don't have anything in your dictionary that's 999 characters large. So you can probably have some better algorithms that improve this algorithm. And it may still be quadratic time. But here we've seen, when we added the character tables that, were the coefficients here are important. It's not just the big O runtime that we care about. So to wrap up here, what are some things that we can do? There have been some common themes throughout this. So one of them is selecting better algorithms. Ones that shorten the the coefficient in your algorithm or the big O runtime. When you're designing and selecting these algorithms, don't just think about the average case, and the same goes for testing them. Think about what's the worst that can happen here. Think about designing for the worst case. And if there's a worst case that you don't like, consider input sanitization if it's not a valid input that you want your users to be giving you. So David and I are co-authors of a tool along with a couple of our coworkers, and we'll be presenting this tool at Arsenal right after this at 11:30. What it does is allows us to generate worst case inputs to some of these common algorithms that we know are used in a lot of applications. So we'll generate the worst case inputs given some requirements. And you'll be able to generate those worst case inputs that hit these corner cases and generate bad outcomes. Another tool is DDoS identification. So David talked about regular expression denial of service, and we have a tool that'll take a regular expression and tell you whether or not it's vulnerable to some catastrophic backtracking. And we're also releasing POCs for the two vulnerabilities we talked about, the PDF and the password checking vulnerabilities. Those are built into ACSploit, which is live now at this GitHub link. So again, we'll be at Arsenal at 11:30 at Station 3. A couple of our coworkers will be presenting there, and we encourage you to check it out. So finally, as a member of the audience, what can you do? Well, for pen testers, you can incorporate AC vulnerabilities into your testing. We hope that ACsploit will help with that, but also coming up with your own test suites and really making AC security a habit. For developers, developing with the worst case inputs in mind. So ask yourself, what is the worst that can happen? We think, if you ask that question up front and not later on, if you don't ask that question up front, you may not like the answer later on. And finally, for researchers, granted, David and I had the years of experience on Stack looking at these types of vulnerabilities. But one of the things that really surprised us was when we looked at these particular targets, it was a matter of days, not months or years, that we were looking at these particular targets and found these vulnerabilities. That leads us to believe that these are really prevalent in other software. And so one of you out there may be the next one to find one. We hope this talk has helped you know some of the warning signs of AC vulnerabilities and be able to identify them better and recognize them for what they are. And when you do find one and see something, say something, tell other people about it so we can get better as a community. So thanks for your attention. We have a blog page up where we'll be posting some more information about these vulnerabilities and AC vulnerabilities in general. There's our contact information, and again, we'll be at Arsenal at 11:30 in the business hall. We hope you'll join us there. And we've got a few minutes for questions from the aisle mics if anyone has any. No, thank you.